Morning, everyone. Weather's fine here. Kind of cool. I want to say around 15 degrees, although it might not even be that today, but it's sunny, so can't complain. Morning, everyone. How are you doing? Questions while we're waiting? Let's wait another minute till everybody comes in. I'm all right. It's cold in Champlain, New York. Maybe the web work will be released today, maybe. Champlain, Ontario. Not sure where that is. Jeremy wants to know, when we approximate to four figures, is the remainder less than 0.0001 or 4 zeros and a 5? We start with 4 zeros and a 5. That doesn't mean it gives us the right answer, as you know. We're going to do another example of that today, time permitting. You do web work on the web work site, not on my courses. There's nothing to submit on my courses. I mean, Rim's asking where we should be at in terms of exercises. I'm giving you the page number, so you know exactly where we are, right? Why don't we start off again where we left off last time? So we're doing exercises from page 764. The question is convergence or divergence. Jeremy suggests that he's seen people use 0.0001 to approximate four figures. Again, it's just a starting point. So it doesn't really matter what you use, as long as you're able to justify that your first four figures are significant. That's fine. Juan, we're going to do another example of that later on. Hopefully we'll get at that. So here's the question. Right? I mean, here, as Sebastian points out, there's no starting point. Now, you understand that this doesn't really affect convergence or divergence, right? You know that we're adding infinitely many numbers. So it doesn't really matter where you start. However, in this case, you don't want to start at 0. Because when n is 0, this is 5 to the 0, which is 1. 1 minus 1 is 0. So we're already in trouble. So you usually, if you really want to give a starting point, you usually start at the first value, which isn't an issue. Really, no, look, I mean, I don't expect you to do anything ahead of time. I mean, you're certainly welcome to. That's not an issue. And I know for a lot of people, this is review. We've seen this before in 141. I mean, this is essentially today is where we stopped, essentially. But yeah. So I mean, I don't expect you to do anything ahead of time, but I do expect you to stay current with the material. So we're doing page from 764 today. After class, you do lots of exercises from that page. We're going to do other stuff as well, so you do that other stuff too. Converges or diverges, you know what you're going to do, right? Last time we introduced the comparison test and the limit comparison test. Here you're thinking to yourself, for large values of n, 5 to the n is the dominant term in the denominator. The -1 is insignificant. So for large values of n, this is going to behave like 6 to the n over 5 to the n. We're going to do a comparison test or limit comparison test with the series 6 over 5 to the n. And what do we know about this series? Antoine is asking if Louis is doing all the exercises at the end of each chapter. Regardless of what Louis answers, the answer should be yes. You should be doing all the exercises at the end of each section. Right? As everybody is pointing out, this is a divergent geometric series. Where 6 over 5 in absolute value is bigger than or equal to 1. Nikki is asking if the web work is going to be multiple choice. I assume you meant exams. So if you did mean exams, the answer is no. All right, so let's do a limit comparison. You know what to do. One of them divided by the other one. Now you have web work, absolutely. And you could do a normal comparison, absolutely. And Professor Fox, who used to teach Calculus 2 with me, I mean, maybe he'll do that again next semester. He was a very big fan of the, he's still a very big fan of the comparison test. And you can do almost all the exercises using the comparison test. So, as an added exercise, try to apply the comparison test to all of these. It's not always the easiest thing, and as I suggested earlier, you have to establish an inequality, and that's always some work. Here, relatively easy. But if you change the -1 to a +1, I'll invite you to do it. I'll invite you to compare the limit comparison test with the regular comparison test. Juan is asking if we could use the integral test here. Well, I going to suggest that this is not a decreasing function. You could still do a comparison test if this was positive. I'll let you do it. Right? Shall we change the question? Right? I mean, in the limit comparison test, whether it's a +1 or -1, it's going to be the same thing, right? The denominator is currently -1. And people were saying you can do a comparison test immediately, and you're right. But what if it's +1? Right? In the limit comparison test, whether it's plus or minus, you'll see that it doesn't make a difference. What are we going to do? First of all, the 6 to the n's cancel out here. So we're left with this. We'll factor out a 5 to the n. These cancel out, and as n goes to infinity, 1 over 5 to the n goes to 0. So whether it's plus or minus makes no difference. The answer is still going to be 1, and consequently, 1 is between 0 and infinity. Both converge or both diverge. This one diverges, so this one diverges as well. As we suggested, you could have done a divergence test, and Juan is actually suggesting that. Very good. Yeah, the limit is not 0, so you're done. Questions here? So I think Gabrielle is suggesting if we let's change this. Let's change it to that with a plus, and it's easy. Right, 0 is less than or equal to 1. So if you add 5 to the n on both sides, and if you multiply the whole thing by 1 over 5 to the n, 5 to the n plus 1, you see that 1 over 5 to the n plus 1 is less than or equal to 1 over 5 to the n. And now if you multiply the whole thing by 6 to the n, you see that 6 to the n over 5 to the n plus 1 is less than or equal to 6 over 5 to the n. And now you're worried that if you just apply a comparison test, the bigger one diverges, so no conclusion about the smaller one. The comparison test doesn't tell you anything here. But this is only because we didn't do it right. Right? This is only because this wasn't the way to go. That's all. This is a mistake on our part. There is a way to work it out with the comparison test. So let's do it. Instead of 0 being less than 1, let's convince ourselves that 5 to the n is bigger than or equal to 1. And I mean, you know that that's correct, right? You know the graph of 5 to the x. And as soon as x is bigger than 0, this is going to be bigger than 1. It's an increasing function. You can take the derivative. You can take the derivative. You can show that it's increasing. So it's going to be bigger than or equal to 1. And now if you add 5 to the n on both sides, which is really 2 times 5 to the n. In other words, 5 to the n plus 1 is less than or equal to 2 times 5 to the n. And if you multiply the whole thing by 6 to the n over 5 to the n, 5 to the n plus 1, what do we get? Which is positive, right? So the inequality remains the same. Here we'll get a 6 over 5 to the n. And on this side, you get 2 times what? 6 to the n over 5 to the n plus 1. I guess I should have included a 2 in here. Let me do that. There you go. So now you see that we have our term, which is bigger than or equal to this divergent geometric series. There it is. Right, so you see, you see why the comparison test is more difficult, right? I mean, you try to get a good relationship, and you got one. I mean, it's a good relationship, but it doesn't give you anything as far as the comparison test is concerned, because this series, albeit a divergent one, is bigger than the series you started out with. So the comparison test doesn't tell you anything. Let's try another one. Somebody's asking, how do we know which way to go for the comparison test? Since we did it 2 ways and got 2 different answers, we did not get 2 different answers. We did not get 2 different answers. Here, we got no answer. We got no answer. The comparison test doesn't tell us anything here. Here, however, it does give us divergence. In what situation would the comparison test be preferable? Well, this is one situation. This is the situation. You're thinking to yourself, for large values of k, the denominator, the k cubed is the dominant term. The denominator behaves like a k cubed. The numerator kind of behaves like a k. So this kind of behaves like a 1 over k squared. And you're, as Rick pointed out, and you're thinking to yourself, if I do a limit comparison with 1 over k squared, which you know converges, let's just see what happens. This, I mean, you might not want to take that down because it doesn't work, and you'll see why. Marie doesn't understand why we multiplied by this term. Well, if you multiply by this term, the right-hand side becomes exactly what you started out with. And that was just, that's exactly what we wanted. Yeah. Jacoby is suggesting a different proof, and that's exactly right. It's fine. Absolutely. Why is there no 1 under the sigma? Well, let's put it. It's fine. All right, let's see what happens here. If you do that and you flip, you get k cubed sine squared over 1 plus k cubed. And if you factor out a k cubed, these cancel out, and as k goes to infinity, this is an infinity, right? This goes to 0. So the denominator goes to 1. And what about sine squared? Well, that's the issue. You know that sine k, as k goes to infinity, doesn't have a limit. So this limit does not exist. And now we're in trouble. Possibly. Well, I mean, somebody's suggesting squeeze theorem, but the thing is, this sine limit doesn't exist. So you're left with sine over 1 plus 1 over k cubed. That limit is not going to exist. That limit does not exist. So don't even bother trying to use a squeeze theorem. The limit itself does not exist. So we have to do something else. And that's where you're going to want to use the comparison test. Right? You're going to want to get rid of this issue. The issue resides in the sine squared. So what do we know? Well, I mean, we do know that sine theta is between -1 and 1. So sine squared of k is going to be between 0 and 1. Rick, there's nothing you can do here. This limit does not exist. The limit does not exist. It's not going towards anything. You're never going to be able to prove that it converges because it doesn't converge. Sine squared is between 0 and 1. And now, hit it. Multiply the whole inequality by k over 1 plus k cubed. And you get k sine squared. Right? This, which is positive, so the inequality remains the same. is less than or equal to this. So if you can show that this series converges, then this series is going to converge. Very nice. And now, to show that that series converges, we do a limit comparison test with the series. Numerator is k. Denominator for large values of k behaves like k cubed, but 1 is insignificant here. We're going to do a limit comparison with 1 over k squared. You could do a second comparison test as well, right? You could show that this is less than or equal to 1 over k squared. Either way. Or you can do a limit comparison. I claim limit comparison is always easier. So let's do it. Of course, you understand that this has the form infinity over infinity. We can use L'Hopital's rule. 3k squared over 3k squared. The limit is easily seen to be 1. You could factor out a k squared, k cubed. It's all the same. Either way, the limit is always going to be 1. 1 is between 0 and infinity. So both converge or both diverge, but this was a convergent p series, where p is equal to 2, bigger than 1. So this converges. And now here, from your comparison, this one converges. So the smaller one converges as well. So this converges by comparison. Cosine squared of n plus pi over 3 is not going to be constant, right? Because it depends on n. I mean, you wrote n, I'm going to assume you meant k. So, yeah, I mean, you cannot treat it as a constant. It depends on k. You could do, wait, could we just do limit comparison with k over 1 plus k cubed? I don't know what you mean by that, Mohammed. Well, we want the limit to exist, right? It has to exist. So just because it's between 0 and 1 doesn't mean the limit exists. Just because your sequence lives between 0 and 1 doesn't mean it has a limit. You could do a comparison test directly with 1 over k squared. There'd be some extra things you'd have to prove. E to the 1 over n, absolutely. The whole thing over n. You know what to do. What are you going to do? right? You're thinking to yourself, as n gets larger and larger, 1 over n goes to 0, e to the 0 is 1. So for very large values of n, the numerator is going to look like the number 1. The denominator looks like n. So we do a limit comparison with the series 1 over n, which diverges. Why does it diverge? We showed, right? I mean, we proved it in class, but it's also a p-series where p is equal to 1, less than or equal to 1. Very good. So let's do it. And when you flip it, you see the n's canceling out, and you just get e to the 1 over n, which is easily seen to be 1. I mean, a very easy example. 1 is some number between 0 and infinity. So both converge or both diverge. This one diverges, so this one diverges by the comparison test. How are we doing here? Questions? Anyone? No? We're good? When we proved p-series, we found 1 over p minus 1. I'm not sure what that means. I think we had proven that p had to be bigger than 1 for convergence. If p was less than 1, we had a problem, and I don't remember if we had actually treated the p equals 1 using the integral test, but if we hadn't, I'm inviting you to do it. There's a distinct cut happening at p equals 1. What I mean by that is the integral for p equals 1 is different than from all the other integrals. You know what happens. So do it. David is suggesting you can use limit comparison test for anything. No, we cannot. We cannot. This example here with the sine squared k, we could not use limit comparison. How are we doing here? In limit comparison, how we choose which one goes in the numerator, which one goes in the denominator, it doesn't matter. It does not matter. What are we doing here? Well, if somebody's suggesting they do much harder ones in grade 12, please give us a hard one. We'll do it. How do we tackle this? In example 34, would you want us to show an inequality? Again, right, limit comparison, that's the beauty of the limit comparison. No inequality to establish. Can you do the comparison test? I'm sure you can. I'm sure you can. Zachary, I realize he's not from our class, but still, certainly welcome to furnish an example. What are we going to do here? Right, that one's a bit tricky. It's not immediately clear. Let me give you a hint, which was not part of the question, but hint. You will recall that as theta goes to 0, somebody's suggesting integral test. I'm going to suggest you want to stay away from that. Because remember, in the integral test, you're going to have sine squared of 1 over x. Had it just been x, fine. But with the 1 over x, that's going to be difficult, to say the least. What is this limit? Limit is 1, thank you. Jeremy was asking, can you take the limit of 1 over n since sine x is continuous? Absolutely. Right, so as n goes to infinity, this goes to 0. Sine of 0 is 0. Perhaps we were thinking the divergence test, a valid proposition, but we immediately see that the divergence test gives you 0, so there is hope for convergence. Limit is 1, right? So what am I suggesting? What's the point? No, it's not 0. It's 1. Limit comparison test with 1 over n squared, very nice. A convergent p-series where p is equal to 2 bigger than n. Absolutely. If you don't see why that is, just go with the flow. We'll see what happens. Yeah, I see a lot of y's here. Let's just go with it for a moment. You'll see why. Sine squared, this squared. I'm going to rewrite this whole thing. Can I take the square out like this? Right? And now, right, from our hint here, this 1 over n, as n goes to infinity, this 1 over n goes to 0. So this is like sine of theta over theta. Right, so this is sine of theta over theta, limit as theta goes to 0. So this thing goes to 1. 1 squared is 1. One is between 0 and infinity. So both converge or both diverge. But this one converges. So this one converges by the limit comparison test. Louis is asking why we decide to compare it with 1 over n squared. Well, exactly because of this. Right? You know this limit is 1, and you're thinking ahead to this idea. With the square, you can pull out a square, and then you have sine theta over theta. The limit is going to infinity, yes, n is going to infinity, but 1 over n is going to 0. Exactly that, Victor. Thank you. Without the hint, is there a trick we could have used? Well, no. No. But now you know. So there it is. The book did not give you a hint. What do we find out with this? Well, the limit comparison tells you the limit should be between 0 and infinity. Rem doesn't understand. How do we get the intuition to these problems? Well, look, practice, practice, practice. You can't do too many questions. It's always the same thing, right? So, I mean, as Gabriel is suggesting, you'll remember that one. Well, that's the thing, I mean, you pick up these tricks along the way. You make these connections. You remember what you did in a previous question. It's all good. Let's look at a midterm type of question. Would be nice to do a recap of when to use each test. That's a problem. There's none of that. Right? In very much the same way as with integration, you never know. Is it integration by parts? Is it partial fractions? Is it trig substitution? Experience dictates what you should at least try first. And it's the same thing here. We have a bunch of tests. Which test do we use? Who knows? If we do a limit comparison, it's interesting. Can we do a limit comparison? Let's see what happens if we do one of them divided by the other. First of all, an could actually be 0, so there's a small issue there, but let's not worry too much about that for now. You can cancel one of them, leaving you with this, and what is that limit? Limit is 0, thank you. Limit is 0. Conclusion? First, good question. Sophie, why is it 0? Why is it 0? We are told that the series converges. So by the divergence test, the stuff you're adding has to go to 0. And then, as Matthew's suggesting, inconclusive. Right? Remember that the limit has to be bigger than 0 and less than infinity. Not equal to 0. And here we have equal to 0. So we're in trouble. It is very close. Very close. But now the answer is actually here. This was the important thing. The limit of an is 0. So for large values of n, an is very close to 0. Exactly that. Right? The ANs are very close to 0, and you know that when you square something close to 0, it's even smaller. And this being positive, you can apply the comparison test. Implies that this converges. Very nice. How do you know it's equal to 0? I suspect you're talking about this. It's from the divergence test. This series converges by assumption. So the limit has to be 0. If the limit was anything other than 0, you would have divergence of the series. How are we doing? Questions? Let's move on to the ratio test. Ratio test. Let series AN be a series of positive terms. Where the limit of the ratio an plus 1 over an is equal to L. What does it mean for the, so Marie is asking why do we have this? And it follows from this. If the limit of an is equal to 0, what does that mean? The limit is the behavior of this for large values. So we're saying that for large values of n, an is going to be very close to 0. So an is going to be less than 1. Very close to 0. But we also know that the ANs are always positive. So it's going to be something between 0 and 1, very, very close to 0. And that's it. Why is it sure that an for large n is between 0 and 1? Well, again, right, I mean, I think we just covered that. Ratio test, blah, 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 equal to L, 1. If L is less than 1, the series converges. If L is bigger than 1, series diverges. If L is equal to 1, the test is inconclusive. Let me, before we take any examples, let me state the root test, because the statement is very similar to that as well. Root test. Right, so again, the same thing and same conclusion. If L is less than 1, the series converges. If L is bigger than 1, series diverges. And if L is equal to 1, the test is inconclusive. All right. Let's take a moment to prove the root test. Proof is nice and easy, and it gives us the importance of, well, you'll see. I don't want to spoil it. What does this mean? If the limit is equal to n, what does this mean? As it did before, right, when I erased it, here, before we had the limit being 0, this meant that for large n, the ANs were close to 0. This means that for large n, this is close to L. Is it buffering? I think it's starting to buffer. Anybody? No? We're good? So for large n, this means that an to the 1 over n is close to L. In other words, for large n, an is close to L to the n. So the series for those large values of n is going to be approximately the series L to the n. Now you see what happens, right? What do we have here? Here we have a geometric series. So the geometric series converges if L is less than 1. The geometric series diverges if L is bigger than 1. And if L is equal to 1, since we're dealing with limits here, right, because of this squiggly equals, it's not a complete proof here, it's just the spirit of the proof, then there's no way to tell. Well, that's what, for large n, right, what are we saying? We're saying that this limit is equal to L. What does that mean? It means that for large values of n, right, because a limit is the behavior. So what we're saying is for large values of n, as n goes to infinity, for large values of n, this term behaves like the number L. This term behaves like the number L. All right. Now that you've committed these to memory, the problem is here we're looking at a limit. So this thing might not necessarily be equal to 1, but goes towards 1. All I'm saying is there are cases where this limit is 1 and the series converges. And there are cases where the limit is 1 and the series diverges. I didn't really say anything. Important, Nikki. We're going to address this question. Converges or diverges? You have options. Now you have options. All I'm saying is, Tiffany is suggesting the integral test, and the integral test absolutely does work here. What I was saying about L equals 1 is, you'll see when you're doing exercises, there are examples of functions, there are examples of series, where this series gives you a limit of 1, but the series actually converges, and others where the series diverges. So with L equals to 1, you don't know. And why don't you know? Because somebody was saying, well, the geometric series 1 to the n diverges, so shouldn't you get divergence? The problem is that we don't have exactness here. We have approximation. And that's where things break down. This is actually not a geometric series, right? But Tiffany was suggesting integral test, and the integral test does work. How can we prove the ratio test? I'm going to invite you to prove it. It's almost the same thing. Try to adapt the proof that we gave here. Rim is suggesting to do L'Hopital's rule. The problem is L'Hopital's rule would be applying the divergence test, and you're welcome to do it. I claim you're going to get a limit of 0. So divergence test will not give you an answer. I'm going to suggest, since we just introduced ratio and root test, I'm going to invite you to do the ratio test. Integral test would have worked. Comparison test would have worked. But let's do ratio. I don't know if it's the D'Alembert criteria. Ratio test, what does ratio test say? We have to look at AK plus 1 over AK. It's the ratio of the next term to the original one, right? In this case, everywhere you see a K in your term, replace with K plus 1. So this is K plus 1 e to the negative K plus 1 over K e to the negative K. All right, let's simplify this a bit. So this is K plus 1 over e to the K plus 1. And this is K over e to the K. You're dividing by a fraction. We're going to multiply by the reciprocal. I think somebody is giving us an answer of E. I think it's slightly off. Maybe you can fix it. The e to the k's cancel out. Leaving you with a k plus 1 over k, and then an extra e here, the 1 over e. 1 over e, very nice. And I mean, whatever you want to do, maybe a L'Hopital's rule here, or factor out a k, or split it into 2 fractions. 3 possibilities. Three possibilities, which all give you the same answer of 1 over e. 1 over e, or 1 over 2.71 something something stuff. The important thing is that 1 over e is 1 over e is less than 1, so series converges by the ratio test. Questions here? There was a question about absolute values, but Louis has answered it nicely. So, I mean, the question came up earlier. How do you know which test to use? And I suggested there wasn't a recipe to know, very much like with integration, right? I mean, you never know. But the ratio test is very well suited to take care of factorials. Charles is asking, how do e to the k and e to the k plus 1 cancel out? Well, they cancel out to give you e to the 1. The k's cancel out here, right? Because this is e to the minus k, and when you add them, you know what's happening. So if there are factorials, usually you might want to try a ratio test. Very nice, Rick. Very nice observation there as well. But it's not an immediate, it's not immediately obvious. You might remember, but we did something like this in class. But if you don't remember, if you don't see it, let's just apply the ratio test. This will show us why the ratio test is well suited to take care of factorials. And it's a nice exercise anyways. But absolutely the answer will be divergence. Let's see what happens. So everywhere you see an n, replace with n plus 1. This is n plus 1 factorial over 100 to the n plus 1, divided by the whole thing, divided by n factorial over 100 to the n. David is asking if we can also do squeeze theorem. Well, I'll let you try it. You can tell me. You can tell me what you get. We're dividing by a fraction, so let's multiply by the reciprocal. This is n plus 1 factorial over 100 to the n plus 1 times 100 to the n over n factorial. Alexandra is asking, shouldn't there be absolute values in the ratio test? Absolutely. There's the answer. Positive terms here, right? In our version of the ratio test, in the version that I wrote down on the board, this ratio test is only applicable to positive series with positive terms. So there's no need for the absolute values. Right, the 100 to the n cancel again. And what happens to the n plus 1 factorial and the n factorial? Let's take an extra step in case you have never seen this before. I've still got the 1 over 100 here. As you know, n factorial is 1 times 2 times 3 all the way to n. N plus 1 factorial is 1 times 2 times 3 all the way to n plus 1. And what is the term that comes before n plus 1? Of course, it's n. So you see what happens, right? The 1's cancel, the 2's, the 3's, everything cancels except the n plus 1. And that's why when dealing with factorials, you often want to use the ratio test. This cancellation is always going to occur in some form or another. Isn't n plus 1 a constant? No, it's not, because, right, I mean, we're looking at the behavior as n goes to infinity. So the n is what's changing. And what's happening here, limit as n goes to infinity? Limit is? You know what that limit is. Limit is infinity. And infinity is bigger than 1. So the series diverges by the ratio test. How are we doing here? Questions? Why doesn't the numerator start at 2 if it's n plus 1? I'm not sure what you're referring to. Oh, n plus 1. I mean, I'm going to assume you mean n plus 1 factorial here. Well, what does n plus 1 factorial mean? Right, if n is 100, this is 101 factorial. 101 factorial is the product of numbers 1, 2, 3, all the way to 101. This is the endpoint. This is the last thing. It always starts at 1. It's 1 times 2 times 3, all the way to whatever that is. Let's do one more. Nicola is suggesting if we start at n equals 1, isn't it 2 times 3 over 1 times, no, I'm not, no. No. If n is 3, what is this? This is 4 factorial. You know what 4 factorial is. It's 1 times 2 times 3 times 4. Forget that it's n plus 1. 4 factorial, there it is. Can you replace by the squeeze test as you usually do for factorials by the ratio test? Well, I think you're referring to when we were just looking at sequences, and that's very interesting. There is a way to deal with sequences by looking at the series instead. Consider this. We have a factorial. So we're going to go with the ratio test, absolutely. Let's try it. This is n plus 1 factorial over n plus 1 to the n plus 1. The whole thing over n factorial over n to the n. A lot of n's. You know what to do? Who knows? Mathieu is suggesting inconclusive. Could be, right? I mean, just because there is a factorial doesn't mean it's absolutely the ratio test. We might still get an inconclusive answer. Let's flip it, see what happens. N plus 1 factorial over n plus 1 to the n plus 1. N to the n over n factorial. Now you saw what happened here, right? I mean, it's again the same thing. So let me cancel these. N factorial, and this factorial is going to cancel, leaving me with just an n plus 1 on top. Then n plus 1 is going to cancel with this 1. So after suitable simplification, I believe we end up with an n to the n over n plus 1 to the n. Is that correct? Is everybody with us here? Stop me. Everybody good? All right. Well, this has the form infinity over infinity. And as Mohammed is suggesting, maybe we could rewrite this as n over n plus 1 to the n, right, since it's the same power. And you know, I mean, you're used to dealing with limits, and you see that this limit, as n goes to infinity, this goes to 1. So this has the form 1 to the infinity. An indeterminate form, for sure. You know how to deal with that. As Marie is suggesting, you're going to take a line. Couldn't you factor out the n and have, you could factor that out. And so the n to the n's would cancel, and you'd be left with 1 plus 1 over n, the whole thing to the n. So you would still have a 1 to the power n in the denominator. So you'd still have to do it in the same way. That is the answer we're going to get. Very nice. Let's do it. See how that arises. First of all, I took a ln and changing the question, so these things are not equal, right? You know the deal there. And by taking this ln, this allows me to bring the power down. As n goes to infinity, this goes to 1. Right? Equivalent rule does that. Ln of 1 is 0, so this is infinity times 0. Another indeterminate form. You know what to do. What are you going to do? We're going to manipulate, to use L'Hopital's rule, the usual trick. Absolutely. 1 over n. You've seen this trick many times. And now as n goes to infinity, this goes to 1. Ln of 1 is 0. And this goes to 0 as well. So now we have a 0 over 0. Very nice. Now we have a 0 over 0. Now we can use L'Hopital's rule. Derivative of the top. Derivative of ln is 1 over. So n plus 1 over n. Times the derivative of the inside, which is easily seen to be 1 over n plus 1 squared. Derivative of the bottom. Everybody with us here? Good, everybody, yes? Good? Why is it 1 over n plus 1 squared? Well, you have to do the work. You have to work it out. It's the derivative of the inside, unless I've made a mistake. Have I made a mistake? With the 1 over 1 plus n, 1 over n plus 1 all squared? Does everybody have that? I think it's good. It's the derivative of the inside, right? You're going to do the quotient rule here. Nah. Thank you, Gabriel. All right, so first of all, I can cancel one of these. I'm dividing by a fraction. Let me multiply by the reciprocal. What do we have here? We have 1 over n plus 1 and negative n squared over 1. Let me cancel one of the n's. And this leaves us with a negative n over n plus 1. As n goes to infinity, this still has the form infinity over infinity, but a quick L'Hopital's rule gives us a negative 1. Now, I rubbed it off, unfortunately, but you remember that we started by taking the ln of the whole thing. We changed the question by taking the ln. So the limit of the original thing we had, which was n over n plus 1 to the n, is consequently, we're going to raise this to the exponential, e to the negative 1, or 1 over e. And this is a number between 1/2 and 1/3. The important thing is that it is less than 1. So the series converges by the ratio test. How are we doing? Questions? Anyone? No, you cannot assume anything. You should always prove it. Let's not say that n over n plus 1 is always less than 1. No. You can, well, yes, you can bring it inside. In other words, this limit is 1, so you have 1 to the infinity. But I mean, you can't bring the whole thing inside and not treat this as infinity. So, yeah. All right. Next time, right, because what have we done so far? We've looked at a bunch of tests, but these are only valid for series of positive terms. I don't want you to recognize, Charles, that this is 1 over e. We need to see the work. So all the tests we've seen so far are for series with positive terms only. Next week, we're going to start looking at series with both positive and negative terms. Yeah, we didn't have time to do an error problem. We'll do one next time. It's all good. So yeah, so we're going to start looking at series with both positive and negative terms and see how that differs from what we've been doing. I will post web work right after class. Well, actually not right after. I have some other things to do today or tomorrow. I'm going to post a web work. Yeah, so either tonight or tomorrow. But it'll be due in 2 weeks. You cannot use that fact that 1 plus 1 over n to the n approaches e. It's not something I expect you to remember by heart, but rather be able to do it. All right, so thank you all for coming. How many questions will the web work be on? 20, 30. It's all good. What about errors in approximation? Are they related to convergence and divergence? Of course, you better have a convergent series. Otherwise, the error doesn't make any sense. Please do not say that n factorial develops faster than 100 to the n. We want to prove it. Again, right? I mean, that's the whole point of math. I don't want you to remember these facts by heart. I don't want you to memorize formulas. I want you to be able to understand and be able to do these exercises. How many attempts? I believe we have 7 attempts per question. So don't waste them. But I mean, it's mentioned. It's mentioned on the actual web work assignment. Thank you all for coming. Have a good weekend, and I will see you on Tuesday.